Swayam Prabha. Digital India. Educated India.
Welcome to Module 51 of Point-Set-Topology Part-I. So as promised last time, let us now start the study of regular spaces and normal spaces. As before in the case of Frechet and Hausdorff, I will first state a theorem which gives you a number of equivalent conditions and then make the definition that a space which satisfies any one of the conditions will be called regular or normal and so on. That is the general plan. So this theorem says the following conditions on topological spaces are equivalent. What are the three conditions? Given a closed set F and a point X away from F in the complement, there exist disjoint open sets UV in X such that X is inside U and F is contained inside V. Just like Hausdorff space, any two points are separated. Here, point and a closed set are separated by open sets. So you can see that this is a one-step generalization of regularity. Okay. Next, for all X belonging to X and open set G such that X belongs to G, there exists an open set H such that X is in H is contained inside H bar, contained inside G. So, in other words, you can say that every neighborhood of a point contains a closed neighborhood. Remember, a neighborhood should be such that there is an open subset contained inside that one, containing the point. Okay, so this H bar will be a closed neighborhood. G was an arbitrary neighborhood. Okay, it need not be open. Actually, here I have said open set G, that's enough because once it's a neighborhood, this G can be replaced by a subset which is open. That's all. The third condition is given a closed set F inside X and a point Y in outside C, similar to the conditions in 1, there exists open sets U and V in X such that Y is in U and F is inside V. All this is same as number 1, but the last part is here it is only disjoint. Here U bar intersection V bar is empty. The third condition is much stronger. Okay. Apparently, but the claim of the theorem is that all the three are equivalent to each other. So let us prove 1 implies 2. All that I do is take F equal to G complement. Okay, G was open, G complement is closed. X was in G, so X is in now F complement. Now apply 1 to get open sets U and V such that X is inside U and F is inside V. And U and V are disjoint. Now take H equal to U, you want to get something here. Since F is contained inside V, V open, U intersection V is empty, it follows that F intersection U bar is empty. Okay. Actually, F intersection H bar is empty, is what I have. This implies H bar is contained inside F complement, and F complement is G. So this is F intersection H bar is empty. Okay. Two implies three. Take G equal to F complement. We get Y in inside H contains H bar contains inside G. This is the property 2, where H is an open set. Okay. Now applying 2 for X belonging to H bar C. H bar is closed. H bar C is open, right? And X is inside that. So what we get? We obtain an open set in Hx, open set, say Hx, such that X belongs to Hx contains Hx bar contains H bar C. Okay, these Hx are different from H. Now take V equal to union of all these Hx, where X belongs to F. That V is an open set containing F. Clearly, Hx intersection H is empty for all X. So V intersection H should be empty. So V intersection H is empty. Hence, Y is inside V bar closure. So applying 2 again, we get an open set U such that Y is in U contained inside U bar contained inside V bar closure. This is a property U. Whenever you have an open set, okay, then Y belongs to U contained inside U bar, there is such a thing. So V bar is closed, complement will be open. So you have to apply 2 at least 3 times here. For the last one, for each point here, you have applied 2 here. Once you have applied this one here also. Okay, this means that U bar intersection V bar is empty. So the stronger condition is obtained. Okay, and 3 implies 1 is obvious. So 1 is taken as definition usually, though 2 and 3 are equivalent. You can use whichever one you like, because that is the easiest to verify. When you want to test whether a given topological space is regular or not, you want to test the simplest thing, easiest thing. So for that matter, I will take 1 as a definition, namely, given a closed set and a point outside it, there are disjoint open subsets containing them X and F respectively, which is similar to Hausdorff's. Only thing is, instead of Y, I have a closed set F. Okay, there is no condition on X. X could be any point, not in F, that's all. Okay, any space which satisfies any of the conditions above, and hence all the conditions above in this theorem, that will be called a regular space. All right. Now I will introduce the normality. The following conditions on a topological space are equivalent. Again, there are 3 of them, almost parallel to 1, 2, 3 of the previous theorem. But the difference is now, given disjoint closed subsets F1 and F2, there exists disjoint open sets U1 and U2 such that F1 is contained inside U1 and F2 is contained inside U2. So you know the immediate distance, immediate difference. Instead of a point and a closed set, I have taken 2 different closed subsets, disjoint closed subsets. So that is the difference. Okay. Then 2 and 3 imitate, just like the 2 and 3 of the previous theorem. Given F inside G, where F is closed and G is open, there exists an open set U in between them, such that F is contained inside U, contained inside U bar, contained inside G. Okay? So this is the condition 2. Given disjoint closed sets F1 and F2, there exists open sets U1 and U2 such that Fi's are contained inside Ui and U1 bar intersection U2 bar is empty. So this is similar to property 3 in the previous definition. Again, the proofs are also similar. So let us go through the proofs again. That these 3 conditions are equivalent. So how to get 1 implies 2, F as F1 and F2 as G complement. You are given F and G are given. G is open, F is contained inside G, right? Take G complement, that will be a closed subset disjoint from F2. Apply 1 to get U1 and U2. Okay, then take U equal to U1. GC, which is the complement of G, is F2 contained inside U2, implies U1 intersection U2 is empty. Therefore, U1 bar, which is U bar, is contained inside G. Okay, so that is 1 implies 2. Similarly, 2 implies 1. This is identical proofs. First, obtain an open set U such that F1 is inside U, contained inside U bar, contained inside F2 complement. The F2 complement is open, and F1 and F2 disjoint means F1 is contained inside F2 complement. So in between, I can put an open set U, such that U is contained U bar contained inside F2 complement. Apply 2 again, okay, to this situation, namely with U bar contained inside F2C. In between these two, you can put one more open set. We get an open set U1 such that U bar contained inside U1, contained inside U1 bar, contained inside F2C. Now you take the complement of U1 bar. U1 bar is closed, so U1 bar is closed, the complement will be open. That take it as V. Then this F2 will be contained inside V. Okay. See here, this is contained in the F2 complement. So when you take the complement, this will be contained in the complement of that. So, and it's easily verified that U bar intersection V bar is empty. Okay. So proofs are identical to the proofs for the regularity. That is why I have put them together in one single place. 3 implies 1 is obvious because 3 is a stronger condition, right? Go back here. Disjoint closed subsets are contained in disjoint open sets. U1 bar intersection U2 bar itself is empty, implies U1 intersection U2 is also empty. And that's all we need in 1. So 3 implies 1 is obvious. All right, now what to do with this regularity and normality? Okay. So what is normality? Anything, any topological space which satisfies 1, 2, 3 of the above theorem. Any one of them, and hence all of them. Okay, normally you can take the first one as a definition, but once you are ready, these two, wherever you have application, you can use any one of them. Proof that 2 implies 3 in this theorem is much easier than the proof for corresponding part of previous theorem. Because you have to do one point by point and so on, and then take the union and so on. So for normality, it was easier actually. Yeah, it's good, yes. Okay, also observe that normality is apparently stronger than regularity. Apparently. Why? Because point and close sets are separated in the regularity. Here, any two close sets are separated. But you have to be careful. Both F1 and F2 must be closed here. Whereas there, X could be any point and the other one is closed. So obviously, we don't have the hypothesis that singleton points, singleton sets are closed. Okay, we don't have that. Therefore, normality may not give you regularity. Okay, so we perceive a major difficulty in deriving regularity from normality. The problem is precisely that singleton set need not be a closed set. Indeed, under this extra hypothesis, namely singletons are closed, which is a Frechet, right? If all the singletons are closed, that is called a Frechet space. So if Frechet if you have, then it's easily seen that normality implies regularity. There can be other hypotheses also under which this may hold. But under Frechet, we know that normality implies regularity. Okay? Regularity, of course, may not imply normality. That is too much to expect. But if you say it is not, then you have to give a counterexample. That is the only way. So you have to give a counterexample. Counterexamples are not all that easy. All right. So we will work on that one, those things now. Okay. In the absence of Frechetness, we shall later see that normality need not imply regularity, which just means that we have to give a counterexample. Of course, it is easily perceived that regularity need not imply normality. Under even put a Frechet condition, it may not. We shall see such an example later. Same problem is there if you try to derive Hausdorffness from regularity, because it looks like I started with the comment that regularity is somewhat generalization of Hausdorffness, right? Any two points are separated by open sets, it's Hausdorffness. Here, point and a closed set is separated, right? So why don't you separate 2 point? Once again, the second point may not be a closed set, right? So second point is arbitrary. So all points must be closed. That means Frechet again. If you have Frechet plus regularity, automatically it will be Hausdorff. Now you see importance of Frechetness. Under Frechetness, see, regularity implies normality. Normality implies regularity and normal and Hausdorffness also, and so on. Okay, regularity implies Hausdorffness. Normality implies regularity. Therefore, it will imply Hausdorffness also. So that may be one of the reasons why Frechet, even in his definition of topology itself, he put that one. Okay. Now, let us work out these things, our habit of checking whether a property is hereditary, co-hereditary, and so on. Frechetness, Hausdorffness, regularity are all seen to be hereditary. Hereditary means what? Take a subspace, it should have same property. Okay. So let us say regularity. Take a subspace and take a point and a closed set. A closed set in the subspace is what? What is a closed subset in subspace? It's some open subset, some closed subset in the larger one intersected with the original subspace. The point is already in the subspace and not inside the smaller set. So it is not in the larger one also. Therefore, you can apply the regularity of the larger space to conclude that there are disjoint open subsets as needed. Now you intersect them with the subspace. So that will give you disjoint open subsets containing the point and the closed set. Okay, so that was the hardest one. Hausdorffness and Freshness, you can do it easily. Okay. So every subspace of a regular space is a regular space. However, you try to do the same thing for normality, you will have problems. Why? Because starting with two closed subsets inside a subspace, there are closed subsets in the larger one. The problem is they may not be disjoint. You start with disjoint closed subsets in the subspace. That means what? There are closed subsets in the larger one. When you intersect with the subspace, they will give you the original sets. But why the new ones inside the larger space should be disjoint? Nobody guarantees you that they are disjoint, and in fact that can happen, and that way the normality may break down. It may not go down to the subspace. Okay. In fact, it happens that normality is not hereditary. So again, we have to construct some example for that. Okay, counter example. Okay. On the other hand, where are these things coming from? You know that, right? Namely, metric spaces. A metric space is Frechet, Hausdorff, regular, and normal also. Very easy to prove. In fact, every subspace of a metric space is metric. Therefore, every subspace of a metric space is also normal. Whereas, subspace of a normal space may not be normal. So, that makes us think about what is going wrong, what is wrong. So, to take a new look at the metric space itself. Okay. So, let us take a look at metric spaces, namely, subspaces are also normal. Why? Okay. So, that is the aspect. Two subsets A and B of a topological space are said to be mutually separated if A bar intersection B is empty and B bar intersection A is empty. So this is slightly, a generalized concept of two closed subsets being disjoint. If A and B are closed subsets, then saying they are separated is the same thing as they are disjoint. That's all, because A bar is A and B bar is again B, right? So there is nothing more than that. Okay, instead of saying closed subsets, start with any two subsets. Putting disjointness is weaker than saying that they are separated. You see, A intersection B may be empty, but A bar intersection B may not be empty. So this is a stronger condition on arbitrary subsets than saying that they are just disjoint. Okay. So this definition is made in the light of the third condition in the normality. You'll see why. Now you see. A typical example of mutually separated subsets, okay, are like this: 0 closed, 1 open, B 1 open, 2 closed. If you take A bar and B bar, they are not disjoint. They will have common point 1. But you take A and B are not closed. Also, A bar intersection B bar is not yet. A and B are mutually separated. Why? A bar is 0, 1 closed and 1 is not here. Similarly, B bar is 1, 2 and 1 is not here on A, in A. So they are mutually separated. Okay. So this is a typical example. Inside Rn, you can construct many such examples. Now, what is that good for? Let us see now. On a topological space X, the following conditions are equivalent. Given two mutually separated subsets A and B of X, there exists disjoint open subsets such that A is contained inside U and B is contained inside B. Now, you see, this is definitely a stronger condition than normality. Why? Because in normality, I started with A and B are closed subsets, right? Then automatically they are mutually separated. This condition is satisfied. But if you start with arbitrary subsets A and B, they are mutually separated. They may not be disjoint. They may not be closed. You can't apply normality to get this one. A contains inside U, B contains inside B. So this statement is definitely stronger than normality. It implies normality, I have shown you, because if start with A and B are closed, they are automatically disjoint, so you will get this one. So condition 1 is stronger than normality. But this theorem says that condition 1 is equivalent to every subspace of X is normal. X is normal is fine. That is the condition 1. Condition 1 implies normality. But more, condition 1 is obviously stronger. What it says? Every subspace of X is normal. Okay, so let us prove this one. Every subspace of X is normal, then you have to show this one also. Okay, so both ways we have work to do here. So let Y be a subspace of X. A and B be disjoint closed subsets of Y. Then I have to produce disjoint open subsets of Y containing A and B respectively. That is my aim. Okay. Now what happens? A and B are disjoint closed subsets. Okay, closed inside Y, not inside X. Therefore, A bar intersection B, which is A bar intersection Y intersection B, because B is a subset of Y. So you can put A bar intersection Y intersection B, associativity of the intersection. But A bar intersection Y, what is this? Can you tell me what is this? All the closure points of A which are already inside Y. Therefore, they will be inside the closure points of A inside Y. Therefore, they are in the closure of A inside Y, but A is closed inside Y. So it is A. So this A intersection B, and A intersection B is empty is the starting hypothesis. A and B are disjoint closed sets. Okay, similarly, B bar intersection A will be also empty, exactly similar. Therefore, when you pass on to the larger space, they will be separated. Okay. Therefore, I can apply 1 to get disjoint open sets U and V in X such that A is inside U and B inside V. Now you take intersection with Y, we are through. All right. Now let us prove the converse. Let A and B be mutually separated subsets of X. Put Y equal to A bar intersection B bar and the complement of that. Remember, A bar intersection B bar may not be empty. If it's empty, you are in a good shape. There is nothing to bother about. So it may not be empty. A bar intersection B is empty and B bar intersection A is empty. So look at Y equal to A bar intersection B bar and its complement. So that's a subspace. Then A bar intersection Y and B bar intersection Y, they are closed subsets in Y. After all, A bar is closed inside X itself. So intersection Y will be closed inside Y. Okay, and they are disjoint now because A bar intersection Y intersection B bar intersection Y is A bar intersection B bar intersection Y, but Y is just the complement of this one, right? So they are disjoint because our choice of Y. There is nothing more than that. By the normality of Y, this is the hypothesis into every subspace is normal. There are open sets U and V inside Y such that this A is inside U, B is inside V. Okay. But what is A and A bar intersection B bar? This is a closed set. So C is complement. So this is an open set of Y. If U and V are open inside Y, they will be open inside X also. So you don't have to fatten them. The same U and V will be open inside X also, right? Therefore, U and V are open inside X also, A contained inside U, B contained inside V. So we are arrived at number 1. All right. So the proof was not at all difficult, but we have to think of, the cleverness here instead of arguing with some points here, points there, and get confused. Okay. So you have to think about this. What subspace should I take? So apply it to the right subspace, you get the answer very easily. Following this theorem, we can now make a formal definition. We have observed that this condition is stronger than normality, so we just call it completely normal, a space that satisfies one of the conditions, and hence both the conditions of the above theorem is called a completely normal space. Okay. So we shall now return to the study of normal spaces. Maybe this is time now. So let us stop here, and normal spaces will be taken up next time rigorously. Thank you.